We're getting into different techniques of taking the derivative instead of having to use that formal definition. And we've been going through the following rules that you should see on your screen. We've looked at the constant rule. Derivative of a constant is equal to 0. We've looked at the constant multiple rule. If you're given some function g of x equals c, and f of x, oh, sorry, I misread that last time too. If you're given some function c times f of x, then the derivative of that function g of x is equal to just c times the derivative of f of x. We looked at the general power rule at f of x equals x to the n being any real number, then when we take the derivative, we bring down our exponent times x and subtract 1 from that exponent. We looked at the sum and difference rule. If we have h of x as f of x plus or minus g of x, then taking the derivative of h of x, it's just the derivative of the first function plus or minus the derivative of the second function. That did not happen, and we saw that it didn't happen for product rule. We couldn't just take, if we had a function equal to a product of two functions like h of x is here, it's not equal to the derivative of the first times second. We showed that, we proved it, we looked at a couple different examples of doing that. We found that the derivative of h of x is equal to the derivative, oh, they do it like I do, of the first times the second function, g of x, plus the first function, f of x, times the derivative of g prime of x. And commutative property holds that sum could be in a different order and be the same thing. Depends on your textbook, your instructor, which order they go in, but they're the same. We didn't have time to prove the quotient rule, but we were able to, I believe, state what the quotient rule was and look at one example of using that quotient rule. So I want to start today by going through and proving why we can use this quotient rule. So again, the quotient rule says if you have some function, let's call it h of x, and that is equal to some function f of x all divided by g of x, where f of x and g of x are both differentiable, g of x can equal 0, then h prime of x is equal to the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator all over the denominator squared. Okay, so order does matter in that numerator. So we have to take the derivative of the numerator first times the denominator minus numerator times derivative of the denominator. Where in the product rule, order didn't matter which one you took the derivative of first, but we have this minus sign here, and so that does affect things. Let's look at the proof of that. And so if we want to find h prime of x, we know by the formal definition, and which we're trying not to do anymore, that the limit as h approaches 0 is equal to it's equal to, let's just write it out first, h of x plus h minus h of x all over h. So that's kind of a weird function because we have h as being called a function and we have a number h getting closer to 0. So I hope you're not getting confused by that. But now when we go back and plug in and we look at this h of x plus h, we're going back into our function f of x and g of x here and plugging in x plus h wherever we see an x. So we would get the limit as h approaches 0 of this h, sorry, not h anymore, f of x plus h all over g of x plus h minus our original h of x function, which we're going to say is f of x over g of x. And then we're putting that all over h. All over, by the definition, h. If we went in here and we did our direct substitution and we plugged in 0 wherever we saw an h, well, we would have in the numerator f of x over g of x minus f of x over g of x. That is 0 all over h, which is 0. So 0 over 0 doesn't tell us anything. Indeterminate form. So we want to manipulate this. This is a complex fraction. So we can manipulate that by multiplying by the least common denominator of the numerator of these fractions. I'm sorry, of the denominator of the fractions in the numerator. So this is g of x plus h all times g of x all over g of x plus h all times g of x. Whole point of multiplying by the LCD is so that our fractions, the denominator cancels, and our fractions go away. So distributing this, g of x plus h cancels for the first, we distribute it first, and we're left with our numerator there, which was that f of x plus h. And we're left with this g of x. Minus, so now when we distribute this to the second fraction, our g of x terms are going to cancel, and we're left with this f of x, our numerator, all times the g of x plus h. And this is all over h times g of x plus h times g of x. Again, if we go in here and we plug in 0 wherever we see it in h, we're going to get 0 over 0, and it doesn't tell us anything. So this is where we have to manipulate it. And the trick in this case was just the same one we used for the product rule, is that we're going to go in here and we're going to add a fancy one. Not one, 0. We usually do the 1. And so in this case, we want to add and subtract the following term to the numerator. And that is going to be f of x times g of x. So if I'm adding and subtracting that, I'm adding just 0. And I'm going to put it in between these two groupings. So let's rewrite that. Pulling down the limit, I have the limit as h goes to 0 of f of x plus h times g of x. Now I'm going to subtract this off, so minus f of x, g of x, plus f of x, g of x, all minus the last piece, which was f of x, all times g of x plus h, all over our denominator, h times g of x plus h times g of x. Okay, so the whole point of this is so that we can regroup this and factor by grouping. So notice that we have 4 terms, groupings in the numerator, and let's factor by grouping. And so we're going to look at f of x plus h times g of x minus f of x times g of x, and we're going to pull out what they both have in common. And so notice both of those terms have this g of x in common. And so we're going to pull out g of x in that numerator. And when we pull that g of x out of the numerator for that first 2 terms, we're left with this f of x plus h. And then we're left with minus f of x. Let's look at the last 2 groupings and let's factor what they both have in common. And so if we look at what they both have in common, f of x times g of x minus f of x times g of x plus h. And so I notice here that they both have a f of x in common. So let's pull those out of those two terms. So we have addition in between here. So I'm going to have a positive. Pulling out an f of x here, we're left with the g of x minus, pulling out the f of x, we're left there with a g of x plus h. All over, well, I could rewrite that all over that single denominator, or let's think of it, because we're going to have to do it anyways. Let's split this up as two separate fractions. So let's put common denominator. So if we added it, we would get back the same thing. So h times g of x plus h all times g of x is down in our denominator. Okay, so let's see if we can simplify either of those fractions, see if we have anything in common. We'll notice that g of x that we pulled out of the first two terms, we have a g of x in the denominator, and those are going to go away. If we look at this, f of x all times, when we pulled out the f of x, that did not cancel anything. Okay, so let's just leave it alone. I can't actually, I don't think I want to do that. Let me just pause for a second. So I think sometimes it's probably helpful for you guys to see what my thinking process is. So I kind of pause there because I'm not sure if I should have canceled out that g of x. And so I'm trying to think about, okay, what are we trying to show? I know with that formula that my denominator has to equal gx quantity squared. I know my numerator, I have to have the derivative times g of x. So let me just think about this for a second. Minus the numerator times g prime of x. And so it almost looks like that's right. Let's just keep going with what I have. And so I'm sure you notice when you're solving problems, you're not totally sure sometimes if where you're going is the correct way, and that's okay. I think that's good to go and try and explore, but then you can also, that helps you when you're doing other problems later. Okay, so let's go back to our limit. I notice our g of x canceled for both of those in our numerator denominator. And so notice that what we have here, and I'm going to kind of rewrite this first fraction. I notice that I see the derivative of f of x there. So the limit as h goes to 0 of my numerator, f of x plus h minus f of x all over h. So I want to be able to write it so that's equivalent to this. So if I pull in front of this another fraction, of how about 1 over this g of x plus h. And then remember limit rules, that we could rewrite this limit of a sum as the limit of each piece. So limit of the first plus the limit of the second. So let's go ahead and do that. And now work and manipulate and look at this piece. So let's do that. If I do that, I know that that second piece has to have in the numerator the derivative of g of x. So let's see if we can manipulate this. Just looking at this. Okay, so plus, I want g of x minus g of x plus h over h. I know that that is by definition the derivative of g of x as the limit as h goes to 0. So let's write a fraction using that derivative. And so doing that, we have g of x minus g of x plus h all over h. And so what would be left is this f of x piece. So let's rewrite this as a different fraction, but multiplying. So it would give us back the same thing, all over this g of x plus h times g of x. Okay, so looking at this, that first piece, and we could break down the limit of the first fraction times the limit of the second fraction by rules of limits, says if I look at the limit as h goes to 0 of this 1 over g of x plus h, that would just leave me with 1 over, let's just write it. That would just leave me with 1 over g of x plus 0. And then this limit of this f of x plus h minus f of x all over h, that right there, that's by definition f prime of x plus, okay, so same idea. I'm going to look at the limit of the first fraction, and I'm going to go in there and I'm going to plug in a 0 wherever I see an h. And so if I do that, I'm left with my numerator, which is just f of x, all over g of x plus 0 times g of x. And then times the limit of the second fraction. Well, this limit of the second fraction, limit as h goes to 0 of this g of x plus h minus g of x minus g of x plus h. That's, and I was a little worried because of this plus sign in between, but now I notice that's not exactly the derivative rule for the derivative. I want g of x plus h minus g of x, and I have here g of x minus g of x plus h. And so we can factor out a -1 from our numerator. So if I pull out a -1 here, since we haven't done it, if I pull out a -1, so this is equivalent of negative g of x minus, wait a minute, this is equivalent of, if I pull a negative out of g of x plus h, g of x plus h, just writing the order different. To make this positive g of x, I'd have to have a minus g of x all over this h. So now when I take the limit, this would equal negative g prime of x because of this minus sign. So I dropped the limit because we went in and we put in 0 wherever we saw an h. So let's just clean that up a little bit. So 1 over g of x plus 0 is just 1 over g of x times f prime of x. So I technically could put that in the numerator. Let's just keep it in black. So we have f prime of x all over g of x plus, but I'm going to pull this negative out in front. So I'm going to put a minus here. So minus f of x times g prime of x all over g of x times g of x. I'm almost to the definition or the rule. If I combine that as one fraction, notice I'm going to get that g squared in the denominator. I need a common denominator, and my common denominator is g of x times g of x. And so I need 1 g of x in the denominator of the first fraction, so multiply it by 1. And so rewriting this, now we have a common denominator. I have f prime of x times that g of x minus f of x times g prime of x all over g of x times g of x, but we can write that as g of x quantity squared. So we just found that that was h prime of x. Another way that we could have written that is, this is the same thing as the derivative d dx of f of x divided by g of x, the quotient rule. So if I was going to write it in this notation, I would write this as in my numerator, means the same thing, d over dx f of x. So it's telling me I'm taking the derivative of my function f of x times g of x plus f of x. Take the derivative of the second function to write it in this Leibniz notation. It's d over dx g of x all over g of x quantity squared. Okay, so we just proved the quotient rule. So if I have a function where I have a polynomial divided by a polynomial, in order to take the quotient, or it doesn't actually have to be a polynomial over a polynomial, a function divided by a function, when we take the derivative, we need to use this rule. Now we're going to look at an example using the quotient rule. So using the quotient rule, we're going to find the derivative of a u. And so it's saying du dx. And so we're going to look at this, du dx. And this is equal to the derivative of our numerator. Maybe we need to write that. So derivative d dx of our numerator, which is 5x plus 1, all times our denominator, which is square root of x, minus our numerator. So in that case, that's 5x plus 1, all times the derivative. So I'm going to say d dx, I haven't taken it yet, of square root of x. And it says put this whole thing all over the denominator squared. So square root of x quantity squared. So let's go through and take the derivative of the numerator denominator, whichever one it's telling us to. So if I take the derivative with respect to x of 5x, well, if I bring my exponent down front, that's 5 times 1, which is 5. And if I subtract 1 from my exponent, that would give me x to the 0 power, which is 1. Plus the derivative of a constant, remember, is 0. So that's the derivative of the numerator. I need parentheses around that whole derivative, all times the denominator, which is the square root of x, minus my numerator, 5x plus 1. So the derivative of the square root of x. So this is where we had to rewrite this in order to take the derivative. So maybe to do this on the side. So if I'm looking at the derivative of the square root of x, it's not in the form that I know how to take the derivative of. I know how to take the derivative of that if I rewrite it in exponential form. And we talked about that if you had some base, maybe the nth root of b raised to the m power, we could rewrite that as b raised to the m divided by n power. So I'm looking at the derivative d dx of x to the 1/2 power. So now we can use that general power rule. So taking the derivative of that, we bring our power down front, 1/2 x, and subtract 1 from our exponent. So we talked about yesterday when we're subtracting 1, if this is a fraction here, make that 1 have the LCD. So my 1, I'm going to have 2/2. So I get 1/2 x to the negative 1/2 power. So that is what this piece is. I'm going to actually even go a little further, and I'm going to rewrite this so that I have a positive exponent. So this is the same thing as 1/2 x to the 1/2, or even better, 1/2 square roots of x. So the derivative of this piece right here is 1/2 square roots of x, all over this denominator squared. Well, square root of x squared is just x. Okay, so we want to kind of clean this up a little bit. So the derivative of u with respect to x, we have this 5 times square root of x. So this is equal to 5 square roots of x minus, well, think of this as 5x plus 1 in the numerator, all over 2 square roots of x, all divided by x. Usually we don't like complex fractions. And so let's get rid of that complex fraction. And we've been doing that when we were looking at the difference quotient before, sometimes. And so if we do that, let's multiply by the least common denominator of all the fractions within. Well, there's only one fraction, so we're going to multiply through by 2 square roots of x, all over 2 square roots of x. So now we have du dx is equal to, well, 5 square roots of x times 2 square roots of x. 5 times 2 is 10, square root of x times square root of x is x. Distribute it to the second piece. The whole point was so the denominator went away, we're left with this minus this 5x plus 1. All over, well, x times 2 square roots of x. We can write that as 2x square roots of x. Almost there. Let's distribute our negative sign. So we have du dx is equal to 10x minus 5x minus 1 all over 2x square roots of x. Can combine like terms in our numerator. 5x minus 10x minus 5x is 5x minus 1 all over 2x square roots of x. So the derivative of u, which was 5x plus 1 all over square root of x, is equal to numerator 5x minus 1 all over the denominator 2x square roots of x. I notice I could rewrite that denominator so it only has a single x by using rules of exponents. So if I did that, this would be the same thing as 5x minus 1 all over 2 times, well, this is x to the first power times x to the 1/2 power. Rule of exponents we would add, so we would get x to the 1 plus 1/2 is 3/2. Okay, so that was using the quotient rule, but I'm looking at u and I see that I have a single term in the denominator. And I notice if I have a single term in the denominator, I could rewrite this so that maybe I wouldn't have to use that quotient rule. I could just use the general power rule and the sum and difference of derivatives. So notice that, let's just look at the same example, but let's go through with it, rewriting it, and show how much faster it could be if you first manipulate your function before you take the derivative. And sometimes we saw that you have to do that in order to take the derivative. So here again, we had u is equal to 5x plus 1 all over the square root of x. So I can break this down as the sum of two fractions. This is the same thing as the first term, 5x all over the square root of x, plus 1 all over the square root of x. So those are equivalent. Have a common denominator, I would sum it, I'd get the numerator summed and the denominator would be the same. Now I can use rules of exponents. So I had mentioned before, rules of exponents are going to be our best friends and very helpful. We need to know our rules of exponents. And so if we have here 5x all over x to the 1/2 power plus 1 over x to the 1/2 power. So you might have been asking yourself, why do we ever need to use these rules of exponents? Here's why calculus is so helpful. I'm not even taking the derivative yet, using those rules of exponents, and if you know them, it goes pretty fast. Division, same base, we're going to subtract the exponent, the larger one is on top, so we're going to keep the x on top. So 1 minus 1/2 gives us 1/2 plus, well, I don't want to have to use the quotient rule. I could use the quotient rule on 1 over x to the 1/2, but I know if I can bring that up into the numerator, which I can by making that exponent negative, I can now, when I take the derivative of this function, just go ahead and use the general power rule. So I have du dx, now taking the derivative, this is equal to, keep the coefficient in front, and now take the derivative of this x to the 1/2. So bring down our power in front, 1/2 x, and now subtract 1 from our exponent. So 1/2 minus 1, so minus 2 over 2, plus the derivative of the second term. So bring our power down front, negative 1/2 x, subtract 1 from our exponent. So negative 1/2 minus 2 over 2. So we get du dx is equal to, well, this is 5 times 1/2 is 5/2. X to the 1/2 minus 1 is x to the negative 1/2 plus a negative, so minus, and this would be x to the negative 3/2 all over 2. It doesn't quite look like what we have right there, but we could rewrite this so that it does. If we brought our negative exponents, or terms with the negative exponents, down, so this is really 5 all over 2x to the 1/2 power. This is minus 1 all over 2x to the 3/2 power. Our LCD there is 2x to the 3/2 power. So really what's missing is I need this to be 3/2. I have to think to myself, 1/2 times plus what would give me 3/2 because of rules of exponents. And so if I multiply both the numerator and denominator by x, I would have my LCD, because 1 plus 1/2 is 3/2. And so now I have, this is equal to 5x in the numerator minus 1 all over our common denominator, which we just got was 2x to the 3/2, which is the same thing we got right there. So there was 2 different approaches. I don't know if there was one was easier to you than the other, but 2 different approaches that we used using different techniques in algebra to find the derivative of u. So I'm not going to prove this. I was going to prove this today. I'm going to, just for time's sake, not prove it and just give it to you. I'm going to give you the derivative of the natural exponential function y equals e to the x. We'll look at it when the base is other than e a little bit later once we learn the chain rule, which is in a couple sections from now. But for now, the derivative of e to the x, this is the easiest one to take the derivative if you can remember it. The derivative of e to the x, or dy dx, is just itself e to the x. So, for example, if I had y equals maybe a coefficient in front, 5 times e to the x, I can use that rule, coefficient times a function that's differentiable is just that constant times that derivative of the function. So dy dx in this case is 5 e to the x. Let's show that's the same thing using the product rule. So let's say with just, and this is overkill for this problem, use the product rule to find the derivative of dy dx. To find dy dx. When y is equal to 5 times the e to the x. Let's show that we get the same thing here. So the product rule, recall, dy dx, says that we take the derivative of our first function. So right now, we're going to think of this as two different functions. We're going to think of 5, that constant, as a function, and we're going to think of e to the x as our second function. So 5, the derivative of 5, so d dx of the first function, 5, times the second, which is times e to the x, plus the first function, which is 5, times the derivative. I haven't taken it yet. I'm just going to write it d dx. I'm going to take the derivative of e to the x. So this is equal to, we'll recall, derivative of a constant, that's 0. So 0 times the second e to the x plus 5 times the derivative of e to the x. If you remember, it's just itself e to the x. And so 0 times e to the x is 0, plus 5 e to the x is just 5 e to the x, which is the same thing we got before. So knowing that rule about the coefficient times a differential function is much easier than having to think of this as going through and using the product as that coefficient as one function and the other piece of that term as another function. But we would get the same thing if we did that. Okay, so now let's look at some of the rules that we've learned and throw this together and try to take the derivative. So we're given a function r, and our function is in terms of the variable theta, and r is equal to e theta times the quantity 1 over theta squared, and then plus theta raised to the negative pi halves. And it wanted us to find the derivative of this function, and we talked about putting it in a function notation. One way was d of what the function is called. Instead of f, it's called r, all over d of what the variable the function is in respect to, which is theta in this case. So I noticed there's a couple different things that I can do in order to take the derivative. If I just took the derivative of how it is written right now, I noticed I'd have to use multiple rules. I would have to use the product rule. I noticed that within the product rule, my second function in here, that first term in that second function, without rewriting that, I would have to use the quotient rule. And the sum which I tend to just not talk about that because just take the derivative of each piece, but the derivative of that sum. So I could do that, no problem. It might take me more time though. So I also noticed that a lot of times if you have a product, we can distribute. So sometimes distributing makes it a lot faster. And so we can distribute that. So if I rewrote this, this is R is equal to E theta all times 1 over theta squared. So this is E theta all over theta squared plus E theta all times theta raised to the negative pi halves. So E theta all times theta raised to the negative pi halves. If I left it in this form, I notice I'm going to have to do a couple things. I would have to use the quotient rule. I would have to use the sum. And here, E theta times theta to the negative pi halves, I would have to use the product rule. I don't know if breaking it down is easier or not. I noticed though I can manipulate this so I don't have to use the product rule, quotient rule, I mean, because this is a single term in the denominator, I can bring this theta squared up into the numerator by changing the sign of the exponent. So using rules of exponents, imagine that. R is equal to e to the theta times theta to the negative 2 plus e theta to the negative pi halves. So I'd have to use the product rule twice here. So I notice again, maybe I should just rewrite this. I'm all for making life easy. I'm sure you guys try to make, whatever you're working with as easy as possible. You don't want to make it difficult, right? Let's factor out that E theta again. So we have theta to the negative 2 power plus theta to the negative pi halves power. So now I just have to use the product rule once. And inside with the second function, I don't have to use that quotient rule. So I manipulated it so we don't have to deal with that quotient rule. So let's rewrite it. So rewriting it without really taking the derivative yet, using the rules of derivative. And I talked about this yesterday, that it's important sometimes to not actually go right ahead and take the derivative once you're in that ready to do that, because sometimes these get so crazy with so many different rules going on that it's better that you write out what rules you're going to be using and then go through and do it so that you're not missing a piece. And so I'm going to take the derivative of the first. So I'm going to look at d theta, it's in terms of theta, of e raised to the theta, times the second, which is theta to the negative 2 plus theta to the negative pi halves, plus the first, well, my first is e theta, times the derivative of the second. So d theta, taking the derivative of the second without really doing it yet, is theta minus 2 plus negative 2 power, theta to the negative pi halves power. So now let's go through, take the derivative, and simplify. So we have dr d theta is equal to, well, the derivative of e to the theta is just itself, e to the theta, times the second, which is this theta to the negative 2 plus theta to the negative pi halves, plus e theta times the derivative of the second. So derivative of the second, we can use that sum rule. And we can use the general power rule. So bringing our power down front, bringing -2 down front. Theta, subtract 1 from our power. So -2 minus 1 is -3. Plus, bring our power down front, -pi12. Subtract 1 from our power. So -pi12 minus 1. I'm going to write that 1 with a common denominator as my -pi12. So -2/2. So I guess we can rewrite it. I notice, and I don't know if you're okay with me doing this right now, but notice that each grouping in between this plus sign, both have an e to the theta. They both, and that's multiplication in between. So we could factor that e to the theta out. So if we pull that e to the theta out from both of these groupings, let's rewrite what we have left. So for this first piece, I have this theta to the -2 power plus theta to the -pi12 power plus, well, I pulled the e to the theta out, so I'm just left with what I had put in blue. And those are all negatives, so I don't know if you're okay with me pulling a negative sign out. Let's make that a minus. 2 to the theta -3. I pull, actually, let's not pull the negative out. So you still be negative. This would be minus because it's minus. Pi12. So subtraction here, -pi -2 in the numerator. So this is theta. I'm going to leave it in exact form. So keep it in the numerator, -pi -2 all over our common denominator 2. I would just look at this and I would think, are there any terms left in here that I can manipulate? And there's not. I could probably manipulate it if I wanted to bring down the negative exponents, those terms with negative exponents, and make them positive. The only thing I think I would clean up would be this 2 to the negative, and that was, I forgot the theta. So let's put the theta there. If that was just 2 to the -3 power, that would have been 1/8, but I forgot to put in the theta in there. And none of those are like terms, so I would just leave it like that. On these, when you're doing my math lab, read what they say if it says it's wrong. It might just be the wrong form. Read and see what form they want things in. Another tip is sometimes if you're not sure what form my math lab wants it is, go view an example. Don't help me solve it, view an example. It will pull up a different example and just scroll to the bottom and see how they wrote their answer. And that could kind of help you in how far do I need to go? Because some of these, I question where, when should I stop? Definitely want to try to get as simplified as possible. But read the directions and they hopefully will tell you, don't have any negative exponents in there. Then I would have changed that. Great example. So it says find the equation for the perpendicular line to the tangent line to the curve y equals x cubed minus 4x plus 1 at the point 2, 1. So we got to go through, read, kind of decipher what it's saying. So I need to find a perpendicular line. And I have to think to myself, what do I know about perpendicular lines? Well, I know two lines are perpendicular. So recall if their slopes are negative reciprocals of one another. So slopes of lines are negative reciprocals of one another. So for instance, if I know my m is equal to a over b, my perpendicular slope, so kind of back in geometry, that upside down capital T means perpendicular. Slope would be the opposite sign. So this was positive, this would be negative. Flip my fraction, b over a. Okay, so I know now that I need to find the slope that's perpendicular to this tangent line. And that tangent line it's the tangent line through this curve at 2, 1. So that tells me I know to find the slope of the tangent line, I have to find the derivative. So I need to find dy dx. I also know because it's at x equals 2. So I needed to find dy dx. So how could I write that? I'm thinking of notation wise. One way was, if it's in this Leibniz notation, I can put x equals 2 here. So that's saying find the derivative of y when x is 2. Well, let's first find the derivative of y. Well, we can use our rules now to find the derivative. So dy dx using my power rule and my sum rule and coefficient rule. So I have derivative of x cubed is 3x squared, bring my power down and subtract 1 from my power. The derivative of negative 4x is minus 4, and the derivative of that constant is 0. So now let's look at dy dx when x is 2. So let's go in here when x is 2, plug it into the derivative, that will give me my slope. And so I would have, this is equal to 3 times 2 squared minus 4. Order of operations, square my 2, get 4. So 3 times 4 minus 4 is 12 minus 4, which is 8. So my slope of the tangent line when x is 2 on the tangent line at x equals 2. Okay, but I want to find the perpendicular line to my tangent line. So all I need to know about that perpendicular line, I need to know what the slope is. Well, if my slope is 8, and I want the perpendicular slope, opposite sign, so negative, and then flip it. So I can think of 8 as 8 over 1. So flipping 8 over 1 is 1/8. So this is the slope I need. And I have a point on the line. They already gave me my point. My point is 2, 1. So now going through and finding the equation of that line, I know a point, a slope. I can use y equals mx plus b, plug in what I know so that I could solve for b. Once I know b and my slope, I have the equation of that line. So y value was 1 here is equal to my slope, which is negative 1/8, times x, which is 2, plus b. So I have 1 is equal to, well, negative 1/8 times 2 is negative 1/4 plus b. Common denominator really quick. So when I add 1/4 to both sides, I have 4/4 plus 1/4. That will be 5/4 is b. So we have that equation of the line. And that equation of the line that's perpendicular to the tangent line of the curve y equals x cubed minus 4x plus 1 at 2, 1 is the following. Y equals our slope negative 1/8 x plus b, which is 5/4. So we just finished up with the techniques of derivatives. We'll learn some more chain rule hopefully next week. But for now, you have all these different rules that you can use, and you don't need to use the formal definition of derivative unless I ask you to.